Let's review the neural netverse. As we can see, it's just kind of this 1 by 1, 2 by 2, 3 by 3, 4 by 4, and 5 by 5 structure. And each one of these can represent a helix. You have sort of a 1 by 1 helix or double helix. Here's a triple helix. Here's a crossing quad helix where you got two double helixes crossing. And then we have this SU5, which I've tried to draw over here as sort of this quintuple helix. You have a triple crossing a double and intersecting this point right over here. So that single point is essentially this U1, and then you get the double helix, which is SU2, and you have the triple helix, which is SU3, and all that gets packed into SU5 because it breaks down like this. Uh, you could see how we could do this. You got SU5 is going to be equal kind of like 3 times 1 plus 2 times 1. And as long as you assign this with a negative a third times 3, and then plus positive a half times 2, we're going to get 0. And so then SU5 actually contains the three groups within it. It's crazy. You got this little tuple, the strong color charge here, the weak isospin charge, and the electromagnetic hypercharge. It's like a little triple. Okay, so this is cool. And just remember that this just breaks out into these decompositions so that we can get our generators or our bosons. So this one just gives us the B boson. This one here gives us the W boson for the weak force. This one here gives us the 8 gluons for the strong force. And then if we go into 4 by 4, we're really looking at gravity. Okay, so this is cool and all, but I'd really like to look at the geometric structure of this because all these numbers don't make a lot of sense unless we look at geometric structure. So I tried to draw it in sort of this way where you have a point. Let's just consider this giant circle to be just a point, T, X, Y, Z. It looks like a nice little circle there, but I don't know, you can call this with a unit circle with a radius of 1. And at that point, it kind of looks almost as if it were a point or something. But anyway, the idea is that you can cover the point. You can cover the point with a Calabi threefold, and the Calabi threefold has 3 dimensions, 3 complex dimensions, which can expand into 6 real dimensions. So you kind of have this 10-dimensional structure here. It looks like it's just T, X, Y, Z, but it's a 10-dimensional structure. 10 dimensions are really important because once you get into the SU5 group here, well, you kind of need you need both a 5 and a 10 to be able to describe all the particles and include the massive neutrino over here. So we have to have this extra 1 over here in order to get the neutrino out of this. Otherwise, we're missing that. Well, that's kind of cool and all, but I'd like to see even further how we build this spin group stuff. So let's look at U1. U1 is just e to the I theta. Well, it doesn't have a double cover. A double cover only starts when you get to SU2. SU2 is actually a double cover of SO3. So if you take just a regular old 3D space, straight up regular 3D space, here's the rotational generators. You got -1 and 1 sort of in these different locations. This is a regular 3D space, but you can cover it with a SU2. And that just means that you're taking the unitary matrix and you're setting it equal to the negative version of the unitary matrix. So you're kind of just dividing SU2 by plus or minus 1, and then you can get SO3 out of that. All that means is that, let's say you have a 3D vector and you're looking at the spin of the 3D vector SO3. You would have 0, 1, 2, or 3 based off of how many dimensions you have. But if you're covering this with a SU2, then all of a sudden you get half spins, So you're just looking at 0, you're looking at a half, you're looking at 1, 3 over 2. So that's how we get these fermion spins from double covering a regular old 3D space. All right, so that's kind of cool. But what does SU2 give us? SU2 gives us this stuff, polyspinners. That means up-down spinners, as in like spin up is 1, 0, spin down is 0, 1. These are non-relativistic, and so you can kind of use this little unitary thing to flip them around and stuff. That's pretty cool. So this is how the SU2 group works. We just get ups and downs, and you can flip them. And they come from this SO3. They come from 3D space. So that's why the arrows are pointing in this direction. In order to get SU2, you had to have 3D space before it. You couldn't you couldn't just pop out of you can't pop three dimensions of space out of SU2. It works the other way around. And so that's why the arrows are pointing this way, indicating that the neural netverse, the informational flow goes towards the smaller dimensions, from larger dimensions to smaller dimensions. So you can see the arrows pointing, and we're sort of approaching this structure. We started from the larger side here, we dip inward, we cross this way, and then we find the point of intersection. So we're just kind of like following the arrows down. So it's cool that SU2 covers SO3, and we get our polyspins. All right. SU3 is a little bit different. We don't really have anything. It's kind of like the U1 where there's no cover of it. So we're going to go straight to SO31. Well, SO31 is very similar to SO3, isn't it? It's just that we added a time into it. So now we've got a 3D space evolving through time. Okay? And the only difference between the SU2 cover, now we have this SL2 complex. And that just kind of indicates that we're using this 3 rotations and 3 boosts. I think that's in SO31. So the 3 rotations and boosts come from the SO31. Just like we had rotational generators in SO3, this describes geometric space, how you rotate in the geometric space. And then this tells you how you rotate in the quantum space. So there's two kind of covers here. We got just a regular old geometric space, which is space-time rotations and boosts. These are the Lorentz transformations. And then you can also consider the cover of it, the spin cover. And like, what the heck is spin doing here? Well, this one's a little bit more interesting. You may not have heard of the group SL2 complex, but we've definitely heard of regular old spinners, possibly. These ones are a little bit more interesting because you got wild spinners, which are 2 complex or 4 real. They kind of look like this. You got the left spinner, which has just 1/2 0. The right spinner works on 0 1/2. So they're kind of independent spinners here. You could take the Dirac spinner, combines the left and the right wild spinners. So that gives you 4 complex, 8 real dimensions. And so this is kind of what the wild spinner or the Dirac spinner kind of transforms as. 1/2 0 combined with 0 1/2. This is massive. This is massless. And then you also have the Dirac equation down here, because this is how the Dirac spinners get used in the Dirac equation. And then you can also have a real condition that sort of pulls a small subset of the Dirac spinners out, as these are specifically real components. So you're kind of taking two of the complex components, forcing them all to be real, and you're also transforming it like this. This is Majorana spinners and Dirac spinners and wild spinners. They all pop out of this SL2C, which is just the 4-dimensional spin group. Well, it's the spin group cover of the 4-dimensional like space-time. So that's kind of cool. And if we want to see a little bit more what these groups really mean, like here's UN, it's just e to the I theta. It's just, we've seen that a million times. SUN is a unitary matrix. Here's like SU2. This is a two-dimensional one, so you have this type of rotation. Uh, you can go into SO, which is the orthogonal, like kind of just this with an extra dimension down here that we're not using. So we're rotating around an axis. You have the SL. This is linear. So you got some real values here. SL and C, this is complex. So you have a difference between the real version, the complex version, kind of look a little bit like this. I think this is just regular old matrices that we're just putting in 2, 3, 4 dimensions, and we see what pops out of it. It's actually not too crazy. But the only problem is, you know, if you try to just go with the basic standard model and you kind of cut this off on 4, 3, 2, 1, and you just go straight with that, you get the same type of image here. It's not nothing crazy. Um, but we're missing a neutrino. The standard model predicts massless neutrinos. Um, so if we want to get a massive neutrino, we have to consider bigger structures of groups because the U1, SU2, and SU3 combined together don't give us a massive neutrino. So we're missing something from the standard model, which is why we have this motivation to try to find the correct group that actually does give us the massive neutrino. And it turns out that, there's this spin 10 group which covers SO10, and that is going to actually give us the massive neutrino. You can see how here we've pulled out from the 5 plus 10. We've got an extra massive neutrino over here. But that might be for another video. I think right now we have discussed what we needed to discuss, how we can cover geometric spaces with spin groups. And when we do that, spinners pop out. And the spinners are the quantum mechanical like rotations that you can do on top of the geometric space that exists. That's just regular old geometry. This is wild. But yeah, here is the visual geometric structure of the neural netverse and how things are collapsing inwards. They're sort of going from the bigger dimensions down to the smaller, into the smaller, into the smaller. And it's all collapsing at one point. This is just a single point. So much stuff is happening at a single point, which is why everything is just like 1 times 1 times 1 times 1. You do that in 2 dimensions, 1 times 1 in 2 dimensions. You do 1 times 1 in 3 dimensions, and you're just getting the same dang point out of it, but you're rotating it. That's why everything looks so confusing, but you're just multiplying by 1. It's so weird. Anyway, hopefully this was an interesting video, and gives us some reason to try to figure out why is spacetime supposed to be 10-dimensional? 10-dimensional spacetime. Doesn't make a lot of sense, but again, we kind of need that 10th dimension to be able to pop out with that massive neutrino.